Let's take a look at velocity vectors. Suppose we have an airplane that in order to have lift, proper lift, it has to fly at a minimum speed of 100 miles per hour. Now, that speed is referenced to the air. So imagine that the air is stationary, no wind. If the plane flies at 100 miles per hour relative to the air, which is stationary relative to the ground, it will have enough lift. So here we have the plane traveling to the left toward a runway, and its speed is 100 miles per hour. Now notice how I wrote this. Okay, we have speed of plane, that's what the P stands for, relative to the air. The air is the medium through which the plane travels in order to get lift, air. It's directed to the left, so we really have here a velocity because it includes both speed and direction. The plane should have no problem approaching that runway and landing. Let's take a look. Okay, now let's say that there's a wind. And let's say the wind is blowing to the right. In other words, toward the plane. We call this a headwind sometimes. And let's say that the wind is blowing at 20 miles per hour. Now, how do we write the subscripts? We would say VA for air relative to the ground. So the air is moving relative to the ground at 20 miles per hour. Now let me make this arrow a bit shorter so that it's proportional to the one I already drew here. Well, not really, but at least it suggests that this is smaller than that. I guess I could make this a little bit longer here. Let's see, 20, 30, 40, 50, 60, 70, 89. Okay, so maybe this. Let's do this. There, that looks better. Okay, so we have VPA and VAG. The air is moving this way, and the plane has to fly at 100 miles per hour relative to the air. Now, if we combine these two velocities, we will get the velocity of the airplane relative to the ground. All right, I'm just going to write here ground, right, because the runway is firmly attached to the ground. So do you see that if you add these two together, since one is to the right and the other one is to the left, we would have to subtract them. So the velocity of the plane relative to the ground is going to be simply 80 miles per hour in that direction. Right? So something like this. So that's how fast the plane will travel relative to the ground, relative to the runway. Notice that that's less than the minimum speed required for lift, but that's okay because this is relative to the ground. This is relative to the air, which is responsible for its lift. Okay, so let's take a look at this. Now suppose we have the same plane, which is traveling at its minimum speed for lift, 100 miles per hour. And let's say it's flying directly toward the runway, as shown. But this time it experiences what is called a crosswind. And the wind is blowing, notice in this case, at right angles to the plane. what's the result? Well, velocities have both magnitude and direction. Since this is directed to the left and this is directed on the board anyway down, perpendicular to this vector here, when we combine these two, which I'm going to do right down here, so if I take this one and combine it to this one. Now when you combine vectors, you always combine them head to tail. So I'm going to take the tail of this and add it to the head of this one. The result is what the plane is going to do. This vector here, which I represented in red, is the velocity of the plane relative to the ground. So let's take a look at that. Now, suppose the airplane wants to land at the runway. Wouldn't the airplane have to direct itself something like that, so that its velocity combined with this velocity gives it a resultant velocity in the direction of the runway? So in landing at this runway, the airplane would have to travel at 100 miles per hour, because that's the minimum speed relative to the air, but in a direction something like that. So that when you combine this with this, as I'm going to show here, so this is your VPA, add that to this. Okay, I made it a little bit longer, just because I didn't draw this to proportion correctly. So this is your VAG. You get a resulting velocity relative to the ground for the plane, which will take it to the runway. So let's take a look at how this looks. And now let's take a look at a real airplane landing in a crosswind. Suppose now we have a river, so I have VWG. What this represents is the speed of the water relative to the ground, let's say is directed this way. Okay, so with the arrow, that's the velocity of the water relative to the ground. So it's a river. And here we have a dock. Okay, and let's say we have a boat which needs to dock over here. Well, if the boat just heads directly toward that dock, won't it travel something like this, right? Because you have the river flowing this way, the boat traveling this way, it's going to miss the dock. Just like an airplane trying to get to a runway in a crosswind, if the pilot doesn't compensate for the wind, the pilot will miss the runway. So what does the captain of this boat have to do? Has to direct the boat something like this. And then it will be able to dock. Okay. Suppose we have a rushing river, okay, VWG. So that's the speed of the water relative to the ground is directed this way, okay? There's the arrow, so we have velocity. Okay? And suppose someone falls into the river who's been out all day, they didn't wear any suntan lotion. Okay, so that's the top of his head. And he falls into the river, and shortly after that, someone in a helicopter flying overhead drops 2 life preservers into the river. One lands here, and one lands there. Okay, so this person's in the river, it's a deep river, life preserver there. Question: if this person wants to save his life, which life preserver should the person swim to first? Or which life preserver should the swimmer swim to, okay, to get to the life preserver as soon as possible? Would it be better for the person to swim to this one, or would it be better for the person to swim to that one? I'll give you some time to think about that. All right, before I answer that, let's take a look at this situation. Here's this ocean liner, again, that I was using earlier. Well, it's not actually an ocean liner, it's a toy. It's a model of an ocean liner. And let's say we have a swimming pool on the ocean liner. There we go. Right there. You see? I think this is blue. Yeah, this is blue. All right, and we have someone in the pool. So I'll just kind of put a little white dot there representing the top of the person's head. And make believe you're on board that ship, okay? And let's say you're standing alongside the pool, and this person's doing laps, okay? So this person swims to there and then back again. Now suppose while the person is doing laps, you realize that the boat is traveling through the ocean like this. Would it make any difference as far as the time it takes this swimmer to go back and forth? Would it make any difference? What do you think? Well, hopefully you said no. It wouldn't make any difference, all right? You understand? It would be like someone walking across the deck, right? Would it make any difference in the time it takes that person to walk across the deck, whether the boat is moving this way or this way? It would not. So going back to this question here, it shouldn't make any difference, right? The swimmer could swim to this inner tube in the same amount of time it would take him to swim to this inner tube. Why? Well, because the inner tube, both inner tubes, and the person in the river are all moving together with the river relative to the ground, just like a pool on an ocean liner. Okay? Imagine that instead of a river, we just have a body of water, like a pond. Like this. Or a swimming pool on an ocean liner. And here's the ocean liner moving this way through the water. So this would be like VBW, right? This represents the ocean water, W. Swimmer just swims back and forth, right? Swims to this life preserver, swims to this life preserver. the motion of the boat itself relative to the ocean has no effect on the time it takes this swimmer to swim to either inner tube. All right, now here's an interesting application of relative velocities or velocity vectors. Here's a view of the Earth. Here's the North Pole. Here's the United States. This is Florida. And there's a rocket ship on a launch pad down here in Florida. Now, from this point of view, the Earth is rotating in a counterclockwise manner. Okay, so make sure you see that first. Now, in order for this spaceship to get into orbit around the Earth, it has to get up to a speed of 8,000 meters per second. That's in order to orbit the Earth. Has to be traveling at 8,000 meters per second. We're going to say more about that in a future unit. We'll talk more about that speed, how that comes about. But that's how fast it has to be traveling. Now, the surface of the Earth, that's how fast it has to be traveling relative to the Earth. Okay, so if you think of the Earth as a stationary object, your reference frame, this will be traveling around the Earth at that speed relative to the Earth, visualizing the Earth as a reference frame, a stationary object. Okay. Now, the surface of the Earth is, let's say, traveling at approximately 400 meters per second relative to the Earth, right? So if you imagine the Earth here as fixed, okay, the surface relative to that fixed point, right, is traveling at 400 meters per second. Okay, so let me help you better understand that. Let's say we have this axis here which represents the pole. Okay, it goes right through the pole of the Earth. So this is what they call a polar axis. So the surface of the Earth is going around that, let's say at 400 meters per second. So to save fuel, do you see that if the rocket ship launches on an eastward path, it will only have to increase its speed by 7,600 meters per second to get up to the required 8,000 meters per second. Whereas if it goes on a westward path, right, it's going to have to increase its speed by 8,400 meters per second, so that when you take into account that the Earth is already rotating in a counterclockwise manner, you end up with a speed of 8,000 meters per second. Well, that will require more rocket fuel. So that's why they launch rockets on an eastward path. And that's also why they launch the big rockets on the East Coast, right? Because if something goes wrong, the rocket will simply crash into the ocean rather than over land. All right? Neat application.